Hello everyone, let's analyze. So today we're going to talk about some applications of the derivative. Specifically, we're going to talk about what the value, the numerical value of the derivative tells us about the underlying function. So we're going to begin with a definition. A function is one-to-one, and you see an example on the bottom left of your screen, if and only if, for each two values in the domain y and z, f of y equals f of z implies that y and z are the same. So if you look at the picture on the left, we see that the only value in the domain y equal to f of y is, well, y. In other words, if you look at y and the mapping of y to f of y, there's no other function, there's no other value in the image equal to f of y for a different value of y, or x. In fact, this may seem familiar to you if you've talked about inverses in other courses. If a function had an inverse, it had to pass a horizontal line test, and that's essentially what we're doing here. If you look at the function to the right, f of x, f of y, and f of z are all equal, but x, y, and z are not equal. So this is not one-to-one, it's many-to-one. In fact, in this domain we're looking at, for this particular value, it's 3-to-1. Three different values get mapped to one same value. It would fail what you might call the horizontal line test. So in order to prove that a function is one-to-one, we need to show that if f of y and f of z are the same, then y and z must be the same. Now, this following theorem will give us a sufficient condition for the one-to-one property, but it's not necessary. In other words, the theorem is not an if and only if statement. So essentially it tells us that if a function is continuous on a closed interval and differentiable on the interior with a non-zero derivative, then the function is one-to-one. Essentially what we're saying is that if the function never has a zero derivative, then the function can't double back and repeat itself. It can't make a U-turn. So suppose f is continuous on the closed interval a to b and differentiable on the interior. Then if the derivative is never zero for all x in the interior, then f is one-to-one. So suppose the derivative is not zero for every interior point, and suppose for the sake of contradiction that f of x and f of y are equal, but x and y are not. Well, by the mean value theorem, there exists a c in the interior whose derivative is there exists a c in the interior, and the derivative of f at c equals the secant slope passing through x and y. Well, since that secant line is horizontal because f of y and f of x are equal, the secant slope is zero, meaning f prime of c equals zero, which contradicts the fact that f prime of x never is zero on the interior. And we have our proof, a very simple, short application of the mean value theorem. So we have our first result about the value of derivatives. If the value is not zero, then we have a one-to-one property. Now let me mention real quick why this is a sufficient condition, but it's not necessary. In other words, it's not necessary that the derivative be always non-zero for a function to be one-to-one. So an example of such a function would be x cubed. X cubed is in fact one-to-one if two numbers cubed are the same value, then those two numbers are, well, the same number. In other words, if a cubed equals b cubed, then a and b are equal. However, the derivative is zero for one point in the domain, specifically at x equals zero. So the condition that the derivative is never zero is sufficient to show one-to-one, but it's not a necessary condition. Now, same hypothesis. Suppose f is continuous on the interior and differentiable, then the following hold. If the derivative is strictly positive, then f is strictly increasing. And if the derivative is strictly negative, then f is strictly decreasing. Now, this result may look very familiar to you. In homework set 13, you proved that if f is monotonically increasing, not strict, but monotonically increasing, then the derivative is non-negative. Here the implication is going the other way, and we're talking about a strict condition. So you might think, how could you take the two results and combine it? Or could it be combined into an if and only if statement? Suppose the derivative is strictly positive for all x in the interior, and let's consider two values in the domain x and y. Let's set x be less than y. Our goal is to show that f of x is less than f of y, that is the strictly increasing property. Well, the secant slope through x and y is equal to the derivative at some point in the interior, and the derivative is, by assumption, positive. Therefore, the change in f from y to x, that is the difference f of x minus f of y, is equal to the derivative, which is positive, times the difference of x and y, which is positive. I'm sorry, negative, because x is less than y. Therefore, f of x minus f of y is negative, implying that f of y is greater than f of x. So since y is greater than x implies f of y is greater than f of x, we've proven our result. Okay, so now we know what happens if the derivative is never zero. We know what happens if the derivative is always positive or always negative. By the way, the proof for the negative result is essentially the same idea, so we omit it here. Now, what happens if the derivative is never positive nor negative? In other words, if it's zero. Well, of course, we know what happens. We get a constant. Let f be continuous on the closed interval a to b, and suppose the derivative is 0 for all x in the interior. Well, then f is constant. Suppose x1 and x2 are two values in the domain, the closed interval a to b, and suppose x1 is the smaller of the two. Now, if we suppose that f of x1 does not equal f of x2, right? We're essentially supposing that we don't have a constant for the sake of deducing a contradiction. All right, so suppose the function is not constant. In other words, f of x1 and f of x2 is different. If they're different, the secant slope through x1 and x2 is non-zero, right? Because there's some change. And if the secant slope is non-zero, then the derivative somewhere is non-zero by the mean value theorem. But the derivative nowhere can be non-zero because the derivative is zero everywhere. And, well, we have our contradiction. Now, suppose f and g are continuous on a closed interval a to b and differentiable on the interior, and suppose that their derivatives are equal. Then they're essentially separated by a constant. There's some real number k, for which f equals g plus k. Again, these are all results that we know. But now we're going to prove it. Well, let h of x be the difference between f and g. Well, then the derivative of h is f prime minus g prime, which is 0 because we're assuming that f prime and g prime are equal. If the derivative of h is 0, then h must be a constant. And if h is the difference between f and g, f is equal to g plus that constant difference. And we've proven the result. That's it for today.